learning right now. So it's worth learning about. The two main reasons why people care about transformers is because they, first of all, are reasonably fast to train. So if you have like a lot of data and a lot of compute, then probably transformers is your best choice because they're parallelizable during training. And second of all, they are pretty good with long-range dependencies. So like in the previous talk, Ahmed was saying that if you use RNN and if you have a long sentence, let's say, the RNN can forget the beginning of the sentence by the time you get to the end of the sentence, right? So it's like hard for it to take in context what happened before. But with transformers, you will see that they can directly access like correlations and like dependencies between any two tokens in a sequence, so they can easily handle all these things. If you care, if you're in your application, these long-range dependencies are important. One particular cool example which came out recently is ChatGPT by OpenAI, which I think they published it like 2 weeks ago. And it's a sequence of language models, because transformers, as I said, was originally designed for text, and like for text applications that are getting better and better. And this is like the latest iteration of this. And it's a chat model. You can chat with it online for free. Check it out; it's pretty cool. And here I tried to ask it for suggestions on like how to make a tutorial on transformers, and it gave me like pretty reasonable plan for this. And the cool thing is that you can converse with it, right? You can tell it like, okay, I like it, but maybe this part is not that good. Can you change it? And it will suggest edits, right? So it's pretty cool. So if we go to how transformers work on the highest level and like how would you use them, maybe without first getting into details how they work inside. If you want to train a transformer to be a chatbot, right, or like some language model, then probably what you're going to do is to collect a large data set of text. And nowadays people typically just use the whole internet as your data set, which is like terabytes and terabytes of text. And then for every sentence you have, you will have, your task is going to be predict the next word in a sentence. And for any sentence you have, you're going to have a lot of kind of input-output examples, right, for training. So like, robot is your kind of input for the model, and then known is the output, like is the thing you want the model to predict. And then for any words in the sentence, you have like an input-output pair, where you kind of slide the window and like go one by words one by one. And the reason why is it a useful idea to predict the next word on the internet corpus is because there are so many things on the internet that to predict the next word well, the model has to be pretty clever, right? Because like on the internet, you can come up with, I don't know, riddles, for example, and then predicting the next word means predicting the answer to the riddle. And maybe there's like murder mysteries where like predicting the next word may mean, predicting the name of the killer or something. So like if you're good at predicting the next word on the entire internet, you're probably pretty clever. So like that's useful. And also if you type a question to this model and then ask it to continue, like what are the next words in this blob of text, then it will probably give you an answer. Because again, on the internet, questions are usually followed by answers, right? So it kind of makes sense that it will sort of work for this. Maybe going back to how this, how do you actually train a model? Then you have this transformer, and you have an input example, and then the transformer outputs you some output, which maybe is not correct right now. Maybe it outputs something random because at first you initialize it randomly and it doesn't know what to do. And then you just optimize, like basically tweak the parameters with optimization, as discussed in the previous talk, to make sure that on this particular example, your model outputs the thing you want, like the next word that is correct in this particular sentence.
So you're supposed to predict one word or distribution of words?
Usually it predicts, like for every word in the dictionary, it predicts the probability that it's next, right? So it will tell you that like, McDonald's is 70% likely to be the next word, and then maybe like landmarks is like 10% likely, and like this for every single word. And maybe again, reiterating on what was already mentioned in the previous talk, because neural networks are typically designed to work with vectors, not with discrete things like text. The first thing you're going to do for this to work is to embed every word, like kind of basically change every word by a vector. So like instead of working with a sequence of words, you're going to work with a sequence of vectors. And to do that, you're going to build this kind of matrix where every word in your dictionary is a row, and then you have, in this kind of cartoonish example, 4 columns, but actually like maybe 500 columns. And then every word in your dictionary corresponds to some particular vector. And then when you have an input sentence, you're going to change all the words into vectors by this kind of mapping, right? So like this dictionary thing defines a mapping. And you may ask, like, where do you get these vectors? Well, the simplest thing to do is just to use random ones, and that probably is going to already kind of work. What actually happens is that you initialize these vectors randomly, and then just treat this matrix as another parameter, like a weight matrix in your neural network. So like that gets optimized with everything else during the training. But maybe that's not that important. Like the important part is that like you just have some mapping from words to vectors, and then you, for any input sentence, you change your sequence of words to a sequence of vectors, right? And then transformer works with a sequence of vectors. And then if you open up this, transformer gray box, then the first thing you'll see that it has a lot of layers, and that's what usually happens with neural networks, that you have maybe like 10, I don't know, 100 layers, and then the more layers you have, typically the more expensive it is to train and to run, but usually the more kind of powerful the model is, right? The more parameters it has, the more flexible it is, like the more complex phenomena it can model. And the idea here is that like every layer kind of builds on top of the previous one, right? So like the first layer can detect simple patterns like that, these two words maybe like, verb and nouns go together, and then like they kind of correlate in a certain way, and then the next layer is going to take the output of the previous layer and yep. Okay. So and the next layer is going to take the output of the previous layer and kind of work on top of it, right? Like, so it will take this kind of updated vectors, which already have more meaning than the original ones, like more kind of correlation data, and then try to build more important, like more complicated concept on top of that. It's like as your vector get processed through the layers, you get more and more meaning inside, in a sense. And then at the end, you predict the thing you want, which is, in this particular case, like predicting the next word. Okay, so again, we opened up the transformer gray box, and it has a lot of layers. So now let's look at the particular layer. Like what's inside a single layer? Inside every layer of the transformer, you have two main things. One of them is called self-attention, and the other one is feed-forward neural network. So this the feed-forward neural network is just a simple, maybe even linear or like a couple of layers small neural network which process every word independently. So it gets its input one vector and then outputs one vector. And usually, and this thing is going to be shared across all words. So it's like the same computation done for every word. But note that if you only had that, then all the words will be processed independently, and then you don't have any correlations or any kind of interdependence between words. So for that, you have the self-attention layer, which task is to kind of find the dependencies between the words. And if you look at a particular example of like how a single word gets processed for a self-attention layer, then probably what you want here is that you want to predict the next word. So like you have an input the word it right now, and also the context words, right? Like the previous words, which you can also use to figure out the next one. And then you want to process it for a self-attention layer, which will kind of mix information from all the context words into the current one. And then you want to use it to finally output the word words. But again, like if you didn't have the self-attention layer, you would only be able to, you will not know anything before the current word, right? So like only based on the current word, it's very hard to predict the next one because you don't know any context. But the self-attention layer kind of task is to mix those things together. And so how can we, again, like we have the current word, we have context, and how can we mix the information from all this word or actually vectors together? Well, the simplest thing to do would be to just sum them up, right? So like this self-attention layer can take as input, all the previous words or word vectors, and just sum them up into a single vector and say that, okay, this vector now somehow contains the information from all the previous ones. And like maybe the neural network will figure out how to use this summation operation to meaningfully combine information from different words. And that can already probably work, sort of, but a more powerful choice would be to sum with weights. So basically, we're saying that we want our neural network to be able to kind of figure out which are the words from the context are important right now for our computation, and then only use those words, right? So like when we look at the word it can correspond to the word team or goal in this particular case. And maybe we haven't yet figured out which of the two ones it is, right? But we probably know from the beginning that it's going to be one of the nouns, right? So like the idea here is that to define some kind of learnable dynamic structure, which will tell us where to look and like what are the important pieces from the context where we want to look. But the question is like, where do they get these weights, right? And the answer to it is to basically define a small neural network which will output those weights for us. And the exact way how it happens is as follows. So okay, we have our current word, it, embedded in a vector. We convert it to a query vector by multiplying it by a weight matrix WQ. And this is basically like a small linear neural network in a sense, right? So like it's a learnable transformation. And this query vector, its kind of purpose is to define what we want from the context. Like it kind of embeds the information about which words from the context we care about. Then we take all the context words and we convert them to key vectors, again, with one learnable transformation, this matrix WK. So now we have our query vector, Q7, and 7 key vectors, K1 to K7. And now we can multiply, like do dot product between these query vectors and key vectors, well, query vector and key vectors, to find out which of the keys are more aligned with the query, right? So like basically query defined, query can say things like, I want to find a noun, and somehow embed that into the weights of this kind of vector. And then the keys will, because the neural network is trained end to end, like everything is aligned, then hopefully the keys will kind of represent somewhere in the information this word is a noun. So like when you do scalar product between them, they will kind of align, and then the scalar product will be large, and that will mean that we want to look at this particular word.
For the organic form of the query vector. With each key here is a linear form of Q.
Yep. Yeah. And it's a learnable quadratic form, right? So like we tune the parameters of it. And then there's one step which is not that important. It's just for numerical stability. You divide it by the square root of the size of the vector, because if the vectors are very large, then these numbers are going to be very large, and it's more stable to divide it. And then you compute the softmax, which is basically, exponent of those numbers, and then just normalize them so that sum to 1. So the idea here is that like the softmax is, it's how to convert numbers to probabilities, how to convert numbers to positive things which sum up to 1, which are kind of, in a sense, proportional to the original things. Like the larger the original thing is, the larger this thing is. And that's basically it. So like this softmax weights is what we're going to use for our attention weights. So we have this kind of learnable transformation, which tells us the softmax weights. And we're going to use those weights as how important this particular word for understanding our current word, right? And so what's left is to just sum the inputs with this weights. Yep.
Can you please go one step back and explain how we get the W? Is it the vocabulary matrix?
Oh yeah. So like, yes.
That's
the thing. So the simplest thing you can do is just to fill it with random noise. And that's probably going to work already, because like the important part is that every single vector should be a different vector. Every single word should be a different vector. But then if you want to improve upon it, you can also use optimization to also tune it, like to change this matrix such that the whole system works better, right? Yeah. But like even just random noise will probably work to some extent. So we have to put these weights, and what's left is to just sum the inputs with these weights, right, to get the output, which is kind of adaptive. But there's one more step, which is which people typically do, which is not, again, that important, but it is done for more like computational reasons, is that we convert our input vectors yet again to another set of vectors, v values, with another learnable transformation. And then finally, we sum this kind of v's with weights. And that, that's not that important. Which instead of summing x's, we can sum v's. And so basically, we added one more linear layer, but that's, it's not the most important part here. The important part is that we have this attention weights, and we sum inputs in some sense with multiplying them by the weights. Yeah.
What is the motivation behind this step? Why we're introducing it?
This last step for this. So I think the main reason is that usually you actually not do one attention like this, but you do several at the same time, because you want to let your network to sort of have like different. So basically, this attention, it tells you where you should look, right? But maybe you should look in different places, right? Maybe you should like in one way think about this word. Maybe to understand this word, you want at the same time find all the nouns in the context, but then at a separate computation, find all the verbs in the context, and then somehow mix those together, right? So usually you do multiple attentions, and then every attention has to be cheap enough to afford all of them, right? So like you just basically shrink these vectors by this transformation. So like that just becomes faster.
If we remove it completely, would it still work?
I think so, yeah.
Thank you.
What if you would swap team and go, like, because you learn the practice, so are all words independent?
That's a great question, and I'll answer it in a few slides. But yes, it's indeed, this whole operation is order invariant. Like it doesn't care about the order of inputs, right? And that's a problem for text. Okay, so if you put this whole self-attention layer together and like, start again from scratch and then put it all together, then we have this. Oh yeah, you see it. We have this matrix of input word embeddings, and this is like 7 rows correspond to the 7 input vectors in our sentence, right? So like we just stack them in a matrix. We multiply it by the learnable WK, which converts these things into keys, and we get a bunch of keys. We do the same thing to getting a bunch of values. Multiply the same matrix by learnable transformation. We multiply the last vector, like our current vector we care about, by the learnable WQ, which get us a query vector. And then we multiply this query vector by the keys and scale it down and like compute the softmax to get the weights. And then finally, we sum the values with the weights here and get the output vector. I hope this makes sense. And you may ask, like, what do we do with the output vector? Well, it gets outputted from the layer, and then it gets processed further by the network, right? So, like, we at every layer we process somehow we get the input vectors, we get the output, we compute the output vectors, and then we pass them to the next layer. And then at the end, we use the last outputs to predict the thing we want. Cool. So if you go back to this picture where we kind of motivated ourselves that we like the word each wants to look at the previous word somehow with the weights, then another way to represent the same picture is to do this, right? So like we have all the words here, and we say that like this thing we want to look at the most, this thing we want also to look at a bit, but maybe not as much. It's just visualization of that space, right? And then actually you can do this not only for the last word, not only for the word it, but you can do it for every word in your sentence, right? So like you can basically fill this matrix. So like you can say that, okay, the word it mostly wants to look at the word team, but the word because also wants to like, I don't know, wants to look at the word score, for example, right? And like for any pair of words, you basically see how much they want to look at the channel, or like how much this word wants to look at this word. And note here that this matrix is lower triangular because we're predicting the next word. So we don't want our network to cheat and to look at the next word, right? So like we want to forbid the network from looking into the future. But that's a design choice. Like if instead of text you used this architecture for protein folding, for example, right? where your input is a sequence of amino acids, and then your output is like locations of those amino acids, then it's fine to look whatever you want, right? So like you will not enforce this constraint that this matrix is lower than one, but that's a design choice you made. And here you can see that, like, the word the, it doesn't have any context. So like it's basically all zeros. It only can use itself to predict the next word. The word team can only look at the, so it's like it's kind of sparse attention. It only looks at the previous word, and then the next words are kind of more interesting. And note that we do not train this thing to be meaningful, right? We do not enforce any constraints on this thing. We just give our neural network ability to use this attention weights, but we never enforce in which way, right? So like we just, the objective for the whole system is to predict the next word, and that's it. Like do whatever it takes to predict the next word. But it turns out that while learning to predict the next word, it also learns to look into the previous words in some way which is sort of meaningful and interpretable by us. Because indeed, if you predict the next word from the word it is useful to look at the word team. So, and that's what actually happens in Transformer, although it doesn't have to, but that happens. And maybe stretching this a bit further, there are papers saying that you can train your transformer to predict something about, let's say, proteins. And then even though you didn't force the transformer for this kind of attention maps to tell you anything useful for you, if you look at those attention maps, they can actually tell you something useful. Like for example, if two amino acids in a protein sequence, interact, if they look at each other during this attention phase a lot, then it probably means that they're, for example, located close in 3D space, right? Because why else would they care about each other? So like these attention maps can be interpretable in practice. Okay. Yep. Let's go.
So in this attention map, should I interpret these labels as just n-1, n-2, or is it dependent on the actual word that came?
Oh yeah, it is dependent. Like if you process, like here, if you process a different sentence, it will be a completely different set of attentions, right? So like it's not, it doesn't learn whether to look at the previous word. It learns like depending on the contents of words, where to look, right? So like here, that's why here we have this kind of keys and values and queries. So like basically this word is the word the, right? And then this vector is probably learned to represent the fact that it's an article, right? And then this thing will probably say that, okay, I'm an article in some sense. Like maybe it's like a one-hot representation. Like, is it an article or not? And then the query vector will say that in this particular case, I really care about what like finding all the articles before. Like it's like a dynamic but learnable system, which looks at the word contents and then understands which words are relevant right now. Yep.
Does the size of the attention map matrix change in the learning, or is it fixed?
It's fixed.
It's fixed. So correct me if I'm wrong. So here you have self-attention can be regarded as basically you're an instance or an object, and you're trying to understand who you are based on your nearest neighbors. Like, is that what it is? Like self. So you're expressing yourself in terms of the weights of those who are most similar to you.
Yeah.
So here it's like words, right? So that's why we call it self-attention. So where is the self coming from here? Because when I hear about self-attention, it's like this about me, but here it's like expressing yourself in function of others.
Yeah.
Right?
I think self refers to the fact that it's like the same sentence. So like we want to understand the sentence in the context of the same sentence. But in principle, if you, for example, translate a sentence from one language to another, when you output the translation, you can attend not to yourself, not to the the current half-finished translation, but to the original language. And that will not be a self-attention because it looks to a different sentence, basically. Yep.
So if I understood well, the output of this self-attention layer is the prediction.
No, it's updated vector, and then you can either predict something from it, or you can add more attention layers if you want to be like, if you want this thing to be more kind of expansive but more expressive as well.
Yeah, but supposing that you have a lot of self-attention layers, and finally you have a prediction. The prediction should be one of different words that can exist.
Yeah,
right?
yeah, that's correct.
And so in this process, I see that the learning is it's concerning of a bunch of words. It's depending to a little sample of words. Where do we use? I mean, how the prediction is done on the word that can be predicted as the continuity of the sentence.
Sorry, I'm not sure I understood the question. So like we process, we have this kind of input vectors. We process them through a bunch of self-attention layers. We have updated vectors which now have information about those words, but in the context of other words. And then we can use a small neural network to predict the next word from it. But yeah, can you please repeat the question here?
Yeah, just I mean, one sentence can have as the correct answer different words.
Oh yeah, that's correct.
So if our model is predicting a word, but it's not really the word that we want,
Yep.
maybe it can be a good word in another context. How do we learn this difference between the word that we want and the other word that can be correct, but it's not the word that we are looking for?
Yeah, so like usually people just don't care about this and hope that it's going to work. I guess in the context of text, that kind of makes sense because on the internet, you can, like if you train on the internet, right, you can find a lot of gibberish, just like random things. And then you're going to learn them because you'll learn on the whole internet. But that's fine because there's not that much gibberish, right? And then maybe you're going to make a lot of mistakes there because it's hard to predict random gibberish, but like whatever, it's like a small fraction of the internet. But then there's also sentences which are ambiguous, as you think. Like there are actually meaningful, interesting sentences which continue in different ways, like meaningfully, right? And then there probably your model will learn to predict, if you like showed enough examples of this, it will probably learn to predict that it's not exactly this word, it's like half-half, like that word or this word. And that's what you would hope to get from it. And then when you sample from the model, when you generate new text, then you'll see that it's like half-half, and then you'll generate one of those words, and then you'll ask the model like, okay, if I generated this first word, what is the next one? And now you know which of the options it is, right?
What is the dimension of the keys and the values compared to the embedded?
I think usually people use like, let's say 512 here, and then they use, let's say 512 divided by 8 here, so like 8 times less, but they do this operation 8 times in every layer. So it's like you shrink those things 8 times, and you repeat the whole computation 8 times with different parameters to make it more powerful.
Is there any like intuition for that?
No, it just something people tried and it sort of worked.
I think there is a disadvantage that if you make them too small, queries and keys, that it's not expressive enough. But if you make them very big, then it does not improve anymore. So they're fairly small. It's queries and keys.
Yeah.
Why is the attention map triangular matrix? The alpha map aren't supposed to be non-zero and physics?
No, again, like because for this task we're trying to predict the next word, right? Like for example, here we're predicting the word A, right? We don't want to look at the word A because it will cheat just and just copy it, right? But if you in your application you do not predict the next word, but you predict something about the whole sequence, then it's fine to let it do non-zero things in the future in the upper half. Yeah.
I'm wondering, I really like the example that you used at the beginning of the presentation with the sentence Rabat is known for
Mhm.
something. And I'm just wondering, how do you actually initialize the prior for the model? Because given that we have the first word, in your case it would be Rabat,
Yeah.
that's really just like a generative sort of model, right?
Yeah.
That sentence can go anywhere.
Yeah.
But if we use Rabat is known for, it's almost like turns it into like a classification task.
Yes.
Like you have a very constrained set of options that you can choose from
Mhm.
for that sentence to make sense. So I'm just wondering, have people considered this, like using a more like, I don't know, generative approach when the sentence starts and then changing that approach to, things that make sense, or like have people incorporated that sort of limitation or constraint in these models, or is it just like left like okay, whatever?
No, I think people just let the model figure it out. And it's like the model actually learns that the first word is pretty kind of ambiguous thing, right? Like you can basically sample almost anything with of course different probabilities, but still like the first word can be almost anything. And then while you go further and further into the generating the sentence, you get more context, and so like the model learns that like, okay, now I have a lot of context, so like the next word should be this.
And so, building on this, is there a tendency for the first word? Like, do certain words always appear as first words, like the, for example?
Yeah, I think so. So like basically, because it's impossible. So we're trying to predict the internet as accurate as possible, right? And if you want to predict the first word of the sentence from the internet as accurate as possible, the best thing you can do is just a statistical model, which basically counts how many V in the internet, you know, as a starting point. And like, that's probably what the model is doing, because it's simple to do, and that's the best thing you can ever do. So like, yeah.
So you said that you don't put explicit constraint on key values in theoretical learning.
Yep.
I was wondering if it learns any spurious correlations, sometimes doesn't make sense.
Oh, of course, yeah. Like all these models suffer from a lot of kind of things you may not want it to do. And like actually, we will in the second half of the tutorial, we will go to graph neural networks, and there you see that like